So, welcome to the webinar on emerging innovation in thermal energy storage. I am Mathew George, and today we are joined by Professor Adarsh Kumar Pandey. And today's conversation will not only dwell into the world of thermal energy storage, but also try to get a glimpse of what it takes to be at the forefront of research in thermal energy storage. Along the way, we'll try to relive the journey traveled by Professor, how he reached here today. And to start off this conversation, I would like Professor Adarsh to introduce himself.
Okay, so thank you, Dr. Mathew. First of all, thank you very much, Atria University and Dr. Mathew for inviting me for this very interesting, actually, webinar. So, later on when I discussed with Dr. Mathew, actually, I was being told that it's not like a regular presentation type of a webinar. It's going to be a kind of a conversation, which I think is more appropriate in that case. Okay, so as far as myself, I'm a Professor Adarsh Kumar Pandey, and currently I'm working as Associate Dean here of Engagement at Sunway University, and the Professor of Renewable Energy, you can say, here in Research Center for Nanomaterials and Energy Technology, the School of Engineering and Technology, Sunway University. So, yeah. And as far as my research area is concerned, so I basically currently I'm working in the area of thermal energy storage using the phase change materials and tackling the different issues of the phase change materials using the nanotechnology. And apart from that, I'm also working in application part of the phase change materials in renewable energy integrations and the buildings and different other applications. And I also work on the solar cells, especially the third generation solar cells, dye-sensitized solar cells. Yeah, that's all about me.
Yes, thank you, Professor. That's a long list, and there's a lot more to Dr. Adarsh than just this, actually. So we'll hope to bring out those information during our conversation. Thank you, Prof. So let us try to take a trip back to your student days. So, are there any particular experiences or teachings from your student time that has influenced your career path or your research in the specialized area of phase change material?
Okay, so Dr. Mathew, as far as let me give you a glimpse of my academic background, actually, from where I have started. So before I jump into how I was influenced by these materials to work on. So actually, I belong to the rural area of India. I belong to Uttar Pradesh and district of Pratapgarh. And if you go to my district, and I purely belong from the village, you will say that. Okay. So why I'm telling you this? Because until the time when we were doing our 10+2, if you see the Google, Professor Google right now, so Professor Google was also founded in 1998, if I'm not mistaken. So until that time, there was very kind of, you don't have the much facilities about the internet where you can Google about it, what are the career path, and look into what to do about the 10th or 10+2. Those things were not available. Only the available thing, your teachers who can guide you what to do after this. So, and until 10+2, we did not have an idea what really we have to do. I just knew that after 10+2, okay, I have to go to the for the competitive exams to get the enter into either in engineering or in sciences. So I was much interested to study on science. So after my 10+2, actually, I did my bachelor's in physics and mathematics from Allahabad Young Christian College, which is the college of Allahabad University. And then I did my master's in physics, specialized because I was very much interested to understand more about the physical phenomenon of not only the materials, but a lot of other things. So I decided to go for the master's in physics. And then, so how I jumped into the thermal energy storage field, let me tell you how. So after my master's, what happened? I got an opportunity to see that, okay, there is one course which is a post diploma in renewable energy technology, which is run by Ministry of New and Renewable Energy, Government of India. I saw one ad, and I was really interested about the renewable energy technology, so I decided to go and give the interview, and I got the admission over there. So it was a 1-year course actually, but during 1 year of course, I was really get to know about these renewable energy technologies in depth, where I studied like many different types of rural energy technologies, all the renewable energy technologies such as solar energy, wind energy, and all these things. So I had an overall idea of these energies. So so it was also not like it was not sudden. I was very much enthusiastic about these materials, to very frank. So after getting this opportunity, after completing that, I got an opportunity to work in one of the research center of the Ministry of New and Renewable Energy as a project fellow. So where I got an opportunity to work on the solar photovoltaic technologies. So solar photovoltaic technologies, when I got an opportunity over there, so I was appointed as a project fellow to work on the batteries actually for photovoltaic technology. Yes. So I started working
Now
there.
battery right now is the big thing, right? Yes.
Yes. So let me tell you how it shaped up all these things. So when I started working on the batteries, then we pointed out that one of the biggest issue in the battery is to look into it's a thermal regulation, because at that time also, if you see, when you integrate the battery to the PV system, and if the temperature of the battery goes up, actually it influences how long it will take to fully charge the battery. Because what will happen, the penetration of current from the solar photovoltaic panel to the battery will be less. So if you have to charge a battery of suppose 40 ampere hour of battery, and it takes if you are giving 4 ampere of current, so it will take 10 hours, right, to get that battery fully charged. If you give 10 amperes of current, it will take 4 hours to get it charged. However, this is ideal condition when the temperature is being maintained at around 25 degrees centigrade. But when you charge that battery and you want to charge it fast, so what happens? The battery temperature also goes up, which affect the battery's life. So when I was working on that, so this was the problem. Then myself and one of my friend both were working under Professor Dr. PC Pant at that time. And then we started tackling this issue by the water circulation around the battery. If you see, one of my first paper which I presented in one of the conference. I went to southern part of India there, and I presented that paper, and that is basically on the how to control this temperature by water circulation. And we actually had designed one setup within the Solar Energy Center. Now it is National Institute of Solar Energy actually. So that is where the foundation thermal management idea has started. So then at that time also, I did not have an idea what is the other way of doing it. We were just simply using the water circulation, which was the active method basically. Then I decided to move on to go for the further studies for my Doctor of Philosophy. And at that time, then I got enrolled in Sri Mathew George University, India. So yes.
Professor, which location was your master's in, actually?
Yeah, I did my master's from Purvanchal University, in Uttar
Purvanchal.
Pradesh. Yes,
Uttar Pradesh.
yes. So
Was it far away from your hometown?
it was not far away. So
It was not
that
far away.
that those were the some constraint and reason, is why I chose, because I wanted to nearby at that time, and because of some uh, family issues, I couldn't go far at that time. So those are some reasons why I decided to go for that college especially.
True.
So when I went for coming back there, when I went for the PhD degree, I decided to go for. So at that time, I thought like which technology where to work on. So it was sure that okay, I'm going to work on the solar energy. I was pretty sure this is the area I have to work on. But at that time also I was not very sure like which area. So when I got my PhD supervisor, I started talking to him. Okay, uh, this is the problem, I want to handle it, and I was working on the battery thermal management. Then he started giving me an idea. Okay, these are the like some of the materials are there, and which has wide variety of temperature ranges, and you can not only do solve this problem, you can solve many other problems using these phase change materials. So that is how this special thermal energy storage area of research came into my life. And I would say that I'm very thankful that this research area came into my life. And whatever I am right now because of this area of research. And this area of research is kind of later on we'll discuss more about it. So yes, there was like a kind of courses I studied during my postgraduate diploma, and then I had hands-on experiences, and then I was
Mhm.
involved in research projects, and I was
Mhm.
guided by my PhD supervisor, who was the main person, motivating person behind it,
Mhm.
Professor S.K. Tyagi, who is in IIT Delhi right now, and another person who influenced me to actually pursue the PhD in this area of research was Dr. V.V. Tyagi, who is in Sri Mata Vaishno Devi University right now. So, these were the people who guided me to delve into this area of research. And the turning point was when actually I got an opportunity at NICE. I handled that project, and then I got an idea. So,
I'm sorry, I'm here.
so yeah, so if as I reflect on my journey as a student, I would say that I'm very very grateful for this invaluable experience I have got throughout this journey. And not only I was guided by the great teachers, and now I also become a thermal energy area academicians working in this area of research. So, however, I would say that I'm continuously eager to explore this area of research. I'm not saying that okay, I have done a lot. Yes, I will continue keep on exploring in that.
Definitely, and that is one attitude and the characteristic that you have, sir. Because that is with always every that you're always ready to learn and ready to explore, and that fearless character is always. And that's a wonderful journey from your village. You've gone to Srinagar to do your PhD, and from there you've done nice. Nice is National Institute of Solar Energy, and from there all the way now in Malaysia. Thank you, sir. And as you mentioned, right now you've been working on phase change material. I think the audience should also know what phase change material is. Can you give a brief description of what a phase change is?
Okay, so phase change materials basically they are kind of a special materials which are being used for storing the thermal energy due to their unique ability to undergo a phase transition. And typically, they change from solid to liquid and vice versa. And during this phase transition of solid to liquid or liquid to solid, they absorb or release the latent heat. So this changing the phase without changing the temperature and storing and releasing the latent heat. Basically, this makes them distinct from other materials which are commonly available. Means you can see that there could be a case if you go for the sensitive heat. So what happens there? There is a fluctuation in the temperature equal to mCp delta T. Means if you have to get the energy, you should be having the temperature gradient, where the temperature changes from one point to the another point. So, but in this case, what happened? Theoretically, the temperature remains the constant. It is the phase which is changing. If it is in the solid phase, so it goes from solid to the liquid phase, and during that time, it absorbs the energy, it stores the energy, and then at the same freezing point, theoretically, I am saying, however, there will be a little changes due to which the phase change materials also have the specific heat. So it comes back from liquid to the solid, and during that transition, it releases the energy, and that energy can be utilized for different several applications. So, however, these phase change materials, I would say that they have different characteristics, such as they have like good latent heat capacity. So these phase change materials are available from sub-zero degree temperature to the very high temperature. In the case of like molten salts, you go, it is more than in fact like 1000 degrees centigrade. From minus to the 1000 degrees centigrade, they are available. First thing, which makes them one of the like very good material, because it gives you an opportunity to use these materials for variety of applications. So because it has got the wide range of phase transition temperature. So if you need, suppose for the cooling applications, so you have the material which are available for the minus, which are available at 0, which are available as 5, 10 degrees centigrade, 20 degrees centigrade, or 25 degrees centigrade. Suppose you want to go for the medium temperature applications like paraffin waxes, right? So you can go for the like 29 degrees centigrade, 30, 35, 40, until it depends on its carbon length. So that makes them like a very good material, because you have got the wide variety of temperature range where you can utilize these phase change materials. Okay. Another property, its thermal cyclability is very good, these phase change materials. Thermal cyclability means these phase change materials work on the phenomenon of changing its phase from one phase to another phase, and back from, suppose it is in liquid, to the solid. So this is how it store and release the energy. And this is the same case when you talk about the electrochemical batteries. It's the same. You charge and discharge. One charge and one discharge is equal to its one life cycle, basically. Suppose you go to the market, and when you buy the battery, what you look into? You say that to the seller, you ask, what is the warranty of this battery? So what do you mean by the warranty? You say that, why do you ask? You want to know that how long it is going to work, right? So how long means when the seller tell you that, okay, the warranty of this battery is 2 years, or suppose 1 year. So this means that 365 cycles it is going to work perfectly. However, 1 year doesn't mean that in a day, if you are charging and discharging, suppose 10 number of times that battery, so it will not last until like 1 year of time. So 1 year means 365 cycles. The same. So any kind of electrochemical batteries, if you go, they will last not more than like 4 years or 5 years of time. They mostly they won't work after that in most of the cases. Okay. However, if you talk about these phase change materials, they are also known as the thermal batteries, because they are doing the same. They are storing the energy. These phase change materials we have tested out until 3,000 cycles. Like, in fact, Dr. Mathew, your research, we have done 3,000 cycles.
Yeah.
Even after 3,000 cycles, we have got that these phase change materials, if you come out with some innovations, they retain their properties. Not these like as a soul, but if you go for some innovation, they can retain their property. So that is good. Means if 3,000 cycles also, if you can retain the properties, which means that you can work 9 to 10 years. And another good property for these phase change materials, they are abundance in most of the cases, and they are economical. So these are these are the phase change materials, and due to these their distinctive characteristics, I would say that PCMs are valued for their effectiveness in managing and utilizing thermal energy in an efficient, controlled, and environmental friendly manner.
Thank you, Professor. I just reiterate. Yes, as you mentioned, there are temperature ranges in the lower range and in the higher range where you have molten salts which can go up to 1,000 degrees Celsius. So for people in the common area, we can look at ice cream. They use ice to actually use it. So that is one form of phase change material that has been commonly used for keeping something cool. And now we have ranges. Over there, it is 0 degrees Celsius. In this case, it can be 25, 30, 50, 100, can go on. So we've been using phase change material in many applications, and we've been trying to keep things cool. We've been trying to keep things warm, and it goes back to what you were saying about battery, where if you keep it at 25 degrees Celsius, the charge would be much more efficient as its temperature increases, and that brings out the application. We want to manage the temperature of the battery, and that is where phase change material can be used. Is there any other applications where we can think of using it? Maybe our buildings or any other application where you have applied it to?
Oh yeah. So okay, these phase change materials, they can be applied in different applications. Okay, let me tell you one thing before you decide. Let me tell you like what are the things you need to consider before you go for the application. Then I'll let you know that where we have applied. So when you are deciding, okay, the phase change materials you have to use, then you need to understand. First of all, you need to consider which application you are going to work for these phase change materials. So the application means that you have to decide what is your phase transition requirement, phase transition temperature requirement. At what temperature, at what grade you need the energy. Suppose my requirement is heating the water for domestic purposes. So heating of water for domestic purposes is roughly around the body temperature we need, like 38 degrees centigrade, right? So if I have to heat the water for and get the 38 degrees centigrade of water, and if we choose the temperature which is having the melting temperature of 50 degrees centigrade. So what will happen? This phase, I mean, whatever the phase change materials, if you utilize that, if that melting temperature is 50, so it will change its phase when it will get the temperature of 50, and it will give you also release back the energy of 50 degrees centigrade. Right. So this first need to understand how to decide. So first thing you need to look into what is your phase transition temperature, what is your application. So this is the most important thing we need to look into. And second thing, second property, what we have to look into the phase change material is whether they are economical or not. They could be phase change materials, and there are phase change materials which are available. Basically, the phase change materials are different types. Okay, like if you take the case of ice only, just now, like how you gave the example of ice cream. So ice is one of the oldest form of phase change materials, which is existing since when we are actually existing, if you can say. So, what happens as the temperature goes to the freezing point, which is 0 degrees centigrade. So the molecules arranged in a way that it solidifies from liquid to the solid state, right?
Yes.
But that ice, if you think that ice you want to use for the heating the water, can you use?
No,
You cannot.
it is not possible. Yeah.
Not possible. Why is not possible? Because it's a freezing and melting temperature is 0, and your requirement is 38 degrees centigrade.
Yes.
You cannot. The same other phase change material, whether you take the paraffin wax or any kind of organic or inorganic phase change materials, so you have to look into first what is its application. So once you decide what is your application, you get to know that what is your phase transition temperature, then you have to work on other properties, such as you look what is the thermoconductivity, what is the latent heat it has got, whether it is thermally stable or not, whether it is chemically stable or not. You check all those properties. Once it is decided, then these phase change materials, you can go for a variety of applications. One application I would say that what we have worked and we have patented, we have filed 2 patents, is using these phase change materials for the thermal regulation in the photovoltaic panels. So I always say that research is not very instant. You have to keep on pursuing that problem for a very long time. I started my career, in 2008 as a project fellow. I was working on that issue, how to regulate the temperature of battery. Meanwhile, we were also thinking that how to manage this temperature. We were not sure about this. And later on, when I graduated during my PhD, I worked a lot on these phase change materials. And then when I graduated and I joined as a postdoc fellow at University of Malaya here, then I started again working on this issue. Means how these phase change materials can be used to regulate the temperature of photovoltaic panel. One very interesting work we have done it, and if you go to the public domain, we have published also, we have filed 2 patents on this application of these phase change materials into the thermal regulation of photovoltaic panel. Why thermal regulation of photovoltaic panel? Because these photovoltaic panels are good. First thing, they can give you electrical energy, but they can, first of all, they can give you only in the daytime, right?
True.
Because solar energy is good. We advocate about the solar energy always. But the solar energy, we need to think about solar energy that it is only available in the daytime. If you talk about the Indian scenario, average solar radiation available is only 5.5 hours throughout the year.
Yes.
It is that you are advocating for the technology which is not available for 18.5 hours. 18.5 hours. And on top of that, in the daytime also, when it is available, it is not constant. It is fluctuating there also, right?
True. Yes.
Morning time it is low, then it goes up, and in between there is a fluctuation, and then goes down, right? So you need a solution where basically you can store that energy, you can utilize in an efficient manner. So to do that, to convert that energy is 2 different collectors. One is photovoltaic collector, one is solar thermal collector. I won't go through basic of that, but let me tell you what we have done in using the PCMs. So when we were using the phase change material, photovoltaic panel, we found that, okay, this temperature is basically harming a lot. It is reducing the efficiency of these panels. So we decided to regulate this temperature of phase change material, photovoltaic panel, as well as first we did only integration of PCM at the back of PV panel, and we got that electrical efficiency has been improved. So later on,
we are maintaining the temperature.
Maintaining the temperature. Yes, because what happens when manufacturers give you photovoltaic panel, suppose it gives 17% efficiency. If you see at the back of the panel, what will happen? you will find that 17% at the standard test conditions. Standard test conditions tell that the temperature should be 25 degrees centigrade and radiation should be, solar radiation should be 1000 watt per meter square. However, if you put this panel outside in the real environmental condition, you can't maintain 25 degrees centigrade. If 25 degrees centigrade is the ambient temperature, you won't find radiation 1000 watt per meter square. So when solar radiation goes up, temperature will go up. So it affects the power output of the panel. So if you have to get the best output from these solar panels, you have to regulate that temperature close to 25 degrees centigrade, close. So one way, you passively apply these material, because you can just simply paste at the back of the panel, and the temperature you can regulate close to 25 or 30 degrees centigrade. So you improve the electrical output. We did one experiment on that. Then what we thought, why we are only regulating the temperature? Because these materials have the property not only regulating, they can store that energy. So why we are regulating? So we applied the thermal collector at the back of the panel, as well as the phase change material, and we went for the active system, circulated the water at the back of the panel. Then what happened? So we, from the same system, same photovoltaic panel, we had the electrical energy, as well as we had the thermal energy. We had the thermal energy storage as well. We had the electrical energy storage using the batteries. So we have designed a system where you can get from the same system electrical energy, thermal energy, electrical energy storage, thermal energy storage. So it's a kind of a complete system we have done. This is one work, one area of application we have done. And then we also worked on the, during especially my PhD, if you search out, we were the kind of a first, if I'm not mistaken, we used phase change materials. You know that UVector tube collector. UVector tube collectors are, if audiences don't know, they are the kind of a solar thermal collectors. So where they are UVected here, and the water, if you go to the water heating system based on the UVector tube collector, is a very famous one. So water goes inside these UVector tubes, and once solar radiation falls on this surface, and that is how this heat is being transferred, and you get the heated water, solar water heating system. So we thought that, okay, water is flowing through this tube. Why not we flow the water through the copper tube, and we utilize that space for keeping these phase change materials? Why? If we are utilizing that space, we can fit in the phase change materials without utilizing any heat exchanger. Within the same system, you can put the phase change materials. You don't require any other system into it. So we flown the water basically through the copper tube and utilize the remaining space for the filling the phase change material into it. So doing that, what happened? So we were able to regulate the temperature, and whenever there was no solar radiation, even in the daytime, the system was still able to give you heated water. So we tested, in fact, in the night time until evening, and until night time also, how long it is perfectly working. So that all, actually we did a lot of experiments. That depends on what is your flow rate of your water into the system. That's all decide. So this is one work we have done. We have also, these phase change materials can be also utilized for the building heating and cooling applications. So another application, what we are right now doing is utilizing these phase change materials for the building cooling application. Basically, we are focusing because given the scenario of Malaysia, we need basically the building cooling applications. So we have designed phase change materials now within the lab. Those phase change materials are kind of a material having the temperature less than 30 degrees centigrade, means close to 25 to 28, where our thermal comfort is there. And we have done a lot of eutectic PCMs. Eutectic means combination of one phase change materials to the another phase change material. Okay, so we have done a lot of work on that. and then we went for the simulation of the building. So when we are, suppose what we have done, we have experimentally come out with what is the thermophysical properties, how we improved using the different approach. Maybe if you allow me, I will explain here as well, or later on we can
Sure, sure.
explain on that part.
That was part of my question actually, because you were mentioning about thermophysical properties, and we
Okay.
need selected thermophysical properties, and how do we improve on that? Because not
Yes.
all
So
materials will have the same.
yes, correct. So okay, let me then focus on the fashion material application part of it. So
No, sure.
then we applied and we proved that if you are going to apply these fashion materials, so the actually it is very energy efficient. Within like 1.5 year, you can recover all costs. And these fashion materials, once you apply to the building, they can work more than 10 years of time, and they can give you cool energy. So this is one application is done, and there are a lot other applications like battery thermal management, waste heat recovery, and the in fact, like one another very good application. One of my student, PhD student, who is Mr. Kalidasan, is going to graduate, and he got the best innovation award on that application part of what. So when we were actually here working surrounding, there were a lot of building construction was going on within the Sunway. So what we found out at that time, like the laborers especially working in the daytime, and the temperature like 36, 37 going, and they were like working like 1 hour, and then they were taking the rest because they were not able to work because of the heat, the temperature.
True, true.
So we decided to basically to help them. So we came out, we designed the face chain materials which can cool their body, and we integrated the face chain materials into the form of a jacket. So within their jackets, whatever they were wearing, that construction jacket, the green color one, yellow one. So
Safety
we put
jackets.
the pocket into it, and the face chain materials packets we provided, and we gave those jacket to the workers. We went there, we were sitting down over there, especially my students, they were going and sitting down for 3 hours, 4 hours. And we found that, okay, at least 3 hours we were able to maintain their temperature. And it is not only maintaining the, when you maintain the temperature, they are in the best condition, and there are a lot of issues you can solve. First of all, you can improve their productivity, because after 1 hour they were taking the break, now they can work. Second thing is being a human being, you are in a condition where like, so you are in a good condition and you are working over there. So this is one application. Another application we have done right now in fetching materials.
So I was just wondering, so has this become a startup idea, and have you tried of actually building from that innovation and going forward?
Yes. And thank you for asking this one. So let me highlight on this. So we took that idea actually, and we presented at different forums, and where the idea was accepted basically by many of the companies, including DHL and some of the companies. So now we are in the process of having the university startup in the name of STG Energy Plus. So, and one of the company from, in fact, from the Singapore venture capital is almost agreed to invest the money in our product, means for to commercialize that product, because the product is ready. We have done all the experiments, we have tested it out. So we already went, we are working on the university startup, and soon you will see that the company is being formalized, and we are selling those products.
Amazing, amazing. I'm very happy to know that it has moved from the research to actual application stage where it's going to come out as a product to the market.
Yes.
And
Yes.
that I think that is the true beauty of research, isn't it?
Correct.
Not staying, and it took such a long time. You started your research back in 2008, and it's right now 2023, and
Yeah.
that is when a product is coming out. So it takes such a long period of time.
Yes, and I keep on Matthews telling to everyone, in fact to my students as well, or any like my buddy researches. I say that, okay, research is not like very instant. If you're going for the instant, okay, you can simply sell something. But if you have to come out with as a researcher, you cannot simply sell something. You have to benchmark, you have to do a lot of studies so that when it goes to the market, okay, it is in the right shape. So, but to take that product, to take that things into the market, it takes time and lot of funding, actually, time and funding. So where a lot of funding agencies and the institution play a very great role in shaping up these research areas. So I'm fortunate enough, like I was getting the continuous research fundings from the external bodies as well as within the universities I was getting, and I was able to take up my research to that level from fundamental aspect to the application part of it where we are right now.
Great, great, sir. So I'll just go back a bit, and as you mentioned, yes, my research had thermal cycling up to 3000, but now you've actually gone beyond that, and you said there was innovation involved in it. So,
Yes.
what kind of innovations were you using to improve the thermophysical properties and so on?
Okay. So that's a good question, Matthew. So we need to understand if when I was explaining about these Christian materials, I told that okay, there are some distinctive properties because of these materials are good and they can be applied in variety of applications. Out of those two, if we focus on thermophysical properties, so in thermophysical properties as well, if you go for the especially the thermoconductivity and the latent heat. So if you go for the thermal conductivity, in most of the cases, thermal conductivity of these phase change materials are comparatively low. So
Right.
if thermal conductivity is low, it means that the heat transfer will be low, right?
Mhm.
So when heat transfer is low, and if you are going for the bulk application, we are talking that, okay, these phase change materials should be applied for the building heating and building cooling. When you are going, suppose for the building cooling application, you do not need these phase change materials in 1 kg or 2 kg. You need in tons. You're talking about the big building. And there, when you are going to encapsulate these phase change materials, you are not going to encapsulate in very tiny capsules. You are going to encapsulate in few 100 grams or 1 kg, 2 kg or 5 kg. So what happens? So if it is like that, then if thermoconductivity is poor, then it will take time to charge that PCM. And the probability is that it will take, if the heating or cooling requirement, the system from which you are charging the PCM, and it is not available that for particular duration of time, the PCM, it is possible that PCM will not be charged. So you need to really find out this solution where you can improve this heat transfer, means thermoconductivity can be improved. So one way of doing is like using the fins. You use the different types of fins people have worked on. I have not worked on the fin-based like heat transfer. So that is one way of doing that. But another very efficient and prominent way of doing is using the nanomaterials. Why nanomaterials? Let me tell you why nanomaterials. Because these nanomaterials, because they are nano, means size is between 1 nanometer to 100 nanometers, very tiny, but if you go, their surface area is very high. So, and surface area is very high, and in most of the cases, the thermoconductivity is very high. So, if I take the example, you understand that one salt hydrate S50, it has 0.2 thermoconductivity. Yeah, watt per meter Kelvin. So, and if you compare one of the nanoparticles, suppose graphene or silver nanoparticle, graphene has 400 watt per meter Kelvin. So you can see that difference in thermoconductivity of these two, and the surface area is very high. So what we are doing, we are synthesizing as well as these nanoparticles, and different types of nanoparticles we have tested out, we are working on, because these nanoparticles are in different dimensions, different shapes, and each behaves differently. So you take the one case, like very simple case, which is being overused, is the graphene, right?
Mhm.
So if you use the graphene has got like 400 watt per meter Kelvin. The thermoconductivity is very high compared to zero point 0.2. So when you infuse those nanomaterials in a very small amount, they can really enhance the thermoconductivity. Means by using the very tiny amount. Suppose you go for like 0.5% of the graphene into fetch-in materials, your conductivity can be improved more than 100%.
Yeah, that's that's a huge jump, actually.
Yeah, a huge jump it can be get. So, however, this varies from material to material. So this is the innovation actually at fundamental scale is needed, which we are doing. And as far as our research group is concerned, we are working on, we have tested out from one-dimensional material to the three-dimensional material. We have tested out how their size, how their shape, these all behaves, and how it can be improved thermoconductivity. Another property need to look into the absorbance.
Mhm.
So
So,
if, yes.
so can you explain what is absorbance? Is it the solar radiation absorbance or the optical
Yes,
resonance?
optical absorbance. Sorry. So optical absorbance, if optical absorbance is good, means you can store that energy quickly, or the more amount of energy can be stored and released. So another point need to look into the improve the absorbance of these material. So that also can be done very well using these nanomaterials. So nanomaterials actually utilizing the nanomaterials into the thermal energy improving the efficiency of the overall system, whether you utilize it for the what you call the building application or renewable energy integration, or you go for the decentralized system or any other applications of it.
Uh, thank you, Professor. I think we are very close to the time, and
Okay.
I'll just so the final one conversation that you want to tell to our students, and what qualities do you look for a researcher to come and work with you, basically? So, what are the qualities that you need so that we can impart that in Atria University also? I'll give my final remarks later on, but first we would like to hear from.
Okay, it's very interesting question, Matthew. Recently I visited China, and I was invited to give a keynote speech over there. So, and after this speech, I visited Guangzhou Institute of Energy and Conservation. It is one of the National Institute of China. So I was interacting there with the PhD students. So I was interacting basically on these thermal energy storage materials. And after my talk, one of the PhD student, he came and he asked me that, sir, what do you think? What is the three qualities which a researcher should be having, or PhD student should be having? So to answer that, I'm telling you, I have a very, very like old answer. I gave, I said, okay, so first thing, what a researcher as a, means you should be having your honesty and your dedication towards the research. How dedicated you are. It doesn't matter you are working in the field of thermal energy storage, or where, in which field you're working in the marketing, sales, as a scientist, or no matter what, your dedication and honesty. This decides, like, means what you will be in the future. So your dedication and honesty plays a very important role. However, as far as mine is concerned, what I look into the any of my student, is how curious they are about the scientists, about the science and technology. Okay, whether they have the strong foundation in the science and engineering or not. I really look into that. because I really believe in that. If you do, your foundation is not good. Foundation means you should be able to critically think on a minute scale as a researcher. It's not only the surface scale. Just like Matthew used to do. I used to like you a lot. Still, I because in your case, whenever you used to take up any type of research, means I used to give, okay, let's work on this. So Matthew used to go each and everything in a very detailed way. So, being a researcher, if you have to pursue a career as a researcher, I would say that that is one of the very important, mm, thing I look into the students. So, yeah, these are the things you should look into the. Now, I basically look for my future student. I don't look like so much on like how academically like you are outstanding. Maybe you have got like 90%, but your attitude towards the research is not that. So it doesn't appeal me, to be very frank. So the one thing which appeals your dedication, your strong interest in science and engineering, that attracts me a lot.
So, thank you, Professor. That was because even I had a very similar idea. I wanted to say that you have to be able to put in hours for the work that you're doing, and it has to be honest. And this is something that I try to tell my students as well. And one thing I really learned from my experience working with you was my first paper. I think after 6 months of putting in the effort, they sent a rejection at 12 a.m. and I was not able to sleep. I was thinking I was not cut out for PhD work. And then next morning, around 6 or 7, I think that is when you realized the mail had come, and he called me up on the day, Matthew, the result has come. Let's look at the improvements that needs to be done, and we'll submit it. You said it so casually. I was like thinking it has been rejected. Then he said it's okay. Rejection is just part and parcel of research. You don't have to worry. It will happen later on. Just put in the time, and that is something that I've been able to take in from you, and I've been trying to put in the time rather than look at the destination where I reach.
Yeah.
And that has been a wonderful experience working with you and under your support. So
Yes, I'm really happy to know that, because yes, being a researcher is we are. I mean, now after like so many years, I can say that I'm immune to rejections. I still get so many rejections.
true,
So whenever and being a student, like when someone comes, like the first when they submit the paper, from their point of view, everyone put 100% of their effort. They really like put in. Being a supervisor, you also give everything to their paper, to their research. Then after like submitting, like after suppose a month or 15 day or whatever, it gets rejected. Then you know that, but students do not know that. Students think that I did put a lot of effort, still the paper has been got rejected. So that is where, like, yes, we need to understand, yes, the acceptance, you straight away get the acceptance. I always say that if you get the comment on your paper, a very critical comment, any reviewer, if you give you like 3 page, 5 page, 10 page comment, that reviewer is really so good to you, doing something good for your career.
true, true.
If your paper is being accepted as it is, you are going to face a lot of challenges later on. See, if you face
Yes.
challenges like initial phase of your life, I mean, you are going to be somewhere like where I'll give you one a very good example of this. When I started my career after my PhD, so I was like, I did 1 year postdoc in Ministry of New and Renewable Energy. Then I was like 2 year postdoc in postdoctoral fellow in University of Malaya, and then research fellow position, and then Sunway University senior research fellow position. So, but I mean, at one point, my friends started telling me that you are holding this fellow position. How long you're going to? hold these positions. But I'm telling you, I have my inbuilt researcher quality. I have so much patience. When I know that I'm doing something right, so I don't deviate because I know that I'm doing something right. Things will come. Just keep on doing that. So I was just keep on doing that. I'm telling you, in Sunway University, if I'm not mistaken, I was like one of the youngest full professor here. I became like within 40 years of my time, I became like full professor. So, and those my friends, some of them is still like assistant professor. So, holding the same position. I'm not like telling this to praise myself, but I streamlining the point where we should understand if you are a researcher, you believe that that idea is good, you keep on putting your effort on that, and things will happen. Things doesn't happen like instantly. It takes time, and it will happen if you are in a right direction.
I think that is an important lesson for everybody. We should not be diverting in one direction.
Yes.
We just have to
Yes.
put in a particular area and just believe that it's going to work, but put in a lot of hours.
A lot. Yes. Put your heart
A lot
into
of
it.
hours.
Yeah.
So it's been a fascinating conversation, and we'll definitely have more conversation offline as well.
Sure.
Anyway, thank you for your time, sir. Thank you, Prof. Adarsh Kumar Pandey. And so
Yeah.
we will end it over here. I think it's one, and
Yes.
you might have to also leave.
Yeah.
Thank you, Professor.
Okay. Thank you very much, Dr. Mathew. And it was really nice talking to you, interacting with you all. And I hope this will give some idea to the my budding researchers, those who are especially the new researchers. They want to do their PhD, and I hope they will get some idea into it. At the end, I would like to end with one word that, okay, if you believe that is correct, just keep on putting your effort, a lot of effort into it, and things will happen. Thank you.
Thank you.
Bye-bye.